Hello, I'm Gyeonglok Yoon. Today, I will be presenting the 5G NR Layer 2 side link protocol stack, which I personally designed and implemented, and we will focus on how the data path is structured. This figure shows a simplified 5G NR Layer 2 protocol stack. The data plane includes SDAP, PDCP, RLC, and MAC, while the control plane consists of PDCP, RLC, and MAC. Through this stack, both user data and signaling messages are transmitted. Sometimes the user plane is also referred to as the data plane since it carries user traffic between the UE and the network. In the G-Node B architecture, the user plane is organized as shown in the diagram. The SDAP and PDCP layers are located in the central unit, while the RLC and MAC layers reside in the distributed unit. Each protocol layer interfaces with both its upper and lower layers. For instance, the MAC layer interfaces with the upper RLC layer through logical channels, and with the lower physical layer through physical channels. At the lowest layer of the central unit, the PDCP entity can establish a dual protocol stack toward another cell in the case of dual connectivity. Recalling the control plane protocol stack from the previous slide and recognizing that PDCP communicates with its upper layer through the radio bearer, we can clearly understand the structure of the dual protocol stack. On the right side, an example illustrates possible user data flow path on the dual connectivity. As shown in A, data may be transmitted to the UE via the master cell group, typically the macro cell, or as in B, via the secondary cell group, typically the small cell. This slide illustrates how user data packets are encapsulated in the user plane. At the top of the protocol stack, the SDAP layer receives IP packets from the upper layers. As these packets pass through each protocol layer of layer 2, they are successively encapsulated with the corresponding protocol headers. With the RLC layer, when user data is prepared for transmission to the MAC layer and further to the PI layer as the transport block. The RLC provides a segmentation function. This function allows the data to be divided into smaller segments that fit within the maximum size of the transport block. Let me summarize the main functions and characteristics of SDAP layer. It maps QoS flows to radio bearers according to the defined quality of service requirements and applies a QFI, the QoS flow identifier, to each IP packet. In NR side link communication, multiple PC5 QoS flows may be mapped to a single SLDRB. So during transmission, each flow is associated with only one SLDRB at a time. For downlink, multiple QoS flows can be shared a single DRB, while in uplink, the mapping is strictly one-to-one. From the UE's perspective, this means N-to-1 mapping for reception and 1-to-1 for transmission, ensuring efficient resource use and consistent QoS management. This diagram illustrates how the SDAP layer handles data in transmission and reception. On the left, In the TX path, each QoS flow is mapped to a DLB, MRB, or SLDRB, and an SDEP header is added if needed. On the right, in the RX path, if an SDEP header is present, the SDEP performs reflective QoS flow mapping, removes the header, and delivers the data to the upper layer. So overall, the SDEP layer ensures consistent QoS handling between uplink, downlink, and side link. This is the configuration used to connect the SDEP's upper and lower interface, the QoS flow, and radio bearer. Through DSL radio bearer config, each radio bearer ID can be associated with the corresponding list of QoS flow ID. In side-link communication, this type of header is utilized. The DC bit specifies whether DSDEP PDU is a data PDU or a control PDU, while the PQFI field identifies the PC5 QoS flow ID associated with that PDU. This slide summarizes the main functions and characteristics of the PDCP layer. It supports both user plane and control plane data transmission, performs header compression, and provides ciphering and integrity protection for secure communication. Each PDCP entity handles data for a single radio bearer, and in the case of a split bearer, it also performs routing between transmission paths. Overall, PDCP ensures efficient and secure data delivery within the 5G NR protocol stack. This diagram illustrates the PDCP processing flow for transmission and reception. On the left, in the TX path, data first goes through sequence numbering and header compression. If required, integrity protection and ciphering are applied, followed by the addition of the PDCP header. Finally, the data is sent for routing or duplication, depending on the bearer type. On the right, in the RX path, the process is reversed. The PDCP header is removed, and if ciphering and integrity protection were applied, deciphering and integrity verification are performed. The layer then handles reordering and duplicate discarding, and finally performs header decompression before delivering the data to the upper layer. In short, this flow ensures the PDCP maintains both a secure and orderly data transmission in the user and control planes. This is the configuration used to connect the PDCP's upper and lower interfaces, the radio bearers and RLC channel. Through the SL radio bearer config, each PDCP configures can be associated with the corresponding RLC configure. Inside ring, these types of headers are used. In the PDCP layer, some header fields are included for ciphering and integrity protection. Unfortunately, in my implementation, the encryption algorithms were not yet developed, so I wasn't able to actually use this field. Now we start the RSC layer. Its core functions include segmentation and reassembly, retransmission and duplication detection, and support for transparent, unacknowledged, and acknowledged mode. In unacknowledged mode, used for Sidewind Groupcast, broadcast, and SL-SR before, a 6-bit sequence number is used. The header fields vary depending on whether the SDU is complete or segmented. And the TX next counter increases with the last segment. In acknowledged mode, the sequence number increases by 1 for each SDU, ensuring reliable in-order delivery. In transparent mode, the RSC stack does not perform any processing. In acknowledged mode, the RSC splits data packets and adds RSC headers before transmitting them over the logical channel. Upon reception, it reads the RSC headers and reassembles the data packet if necessary. In acknowledged mode, the retransmission feature is added on top of unacknowledged mode. In this case, the RSC follows the AIQ, Automatic Repeat Request Protocol rules. Like the previous layers, the RSC can also configure which interface is used to transmit data packet to the upper and lower layers. The upper layer is identified by the RBID, Radio Vero ID, and the lower layer identified by LCID, Logical Channel ID. Both are configured through DSL-RSC Vero config. In unacknowledged mode, the following header types are used. Pay attention to the segmentation info, sequence number, and segment offset field. These fields are used in the RSC-UM function. In acknowledged mode, the following header types are used, unlike in UM. Additional bits such as data control and polling bit field are included. To implement RSC AIQ, 3Qs along with segmentation, routing, and reassembly processes are required. In the diagram, RSC-TX is the queue for newly transmitted data packet. RSC-retrans is for retransmission, and RSC-RX is for received data packet. Both the RSC-retrans and RSC-RX queues have TX and RX windows, which are adjusted according to the 3GPP-TS 38.322 specification. A detailed explanation of their operations will be provided in the next slide. This figure illustrates SDU delivery in RSC acknowledged mode. At time T0, the transmitter sends PDUs N, N plus 1, N plus 2, and so on within the transmission window. Some PDUs are acknowledged, while others are still pending. At time T1, PDUs N plus 1 and N plus 2 are transmitted, but only PDU N plus 2 arrives at the receiver. Since PDU N plus 1 is missing, the receiver cannot advance its reception window and start the T reassembly timer. Before the timer expires, the missing PDU N plus 1 arrives at time T2, allowing reassembly of the complete SDU. And the window is then advanced and the timer is stopped. Duplicate PDUs such as retransmitted N+2 are detected and discarded by the RLC. This process ensures reliable in-sequence data delivery between transmitter and receiver. This figure shows retransmissions of missing PDUs in RLC acknowledged mode. At time T3, PDUs up to N+5 have been transmitted, but only N+5 arrives at the receiver. PDUs N+3 and N+4 are missing. The receiver starts the T reassembly timer. When the timer expires at time T4, the receiver sends a control PDU containing a status report that lists the missing PDUs. Upon receiving the status report at time T5, the transmitter advances the transmission window and retransmits PDUs N+3 and N+4. These retransmissions are correctly received, and by time T6, all PDUs have been successfully delivered. Finally, the transmitter requests a final status report to confirm complete delivery up to PDU N+5. This mechanism ensures reliable delivery and prevents unnecessary retransmission delays. This slide shows the key functions of the MEC layer. Its main roles include channel mapping, multiplexing, HAC retransmission, scheduling, and layer 2 ID filtering. The MEC control elements manage scheduling reports, random access, timing advance, and component activation or deactivation, all essential for efficient and reliable communication. This diagram shows the architecture of MEC layer. On the transmission side, data first goes through logical channel prioritization, followed by multiplexing and then HAC processing before being sent to the physical layer. On the receiving side, the process is reversed. HAC handles retransmissions. Layer 2 ID filtering identifies the correct barrier, and the multiplexing separates data for each logical channel. At the center, the control block coordinates all these functions, managing scheduling, reporting, and timing control between the transmitter and receiver. Together, these components ensure reliable and efficient data transfer in the MEC layer. The logical channel can be identified by the LCID, logical channel ID, specified in the SL RLC veroconfig. The MEC layer subheader is structured as shown here. Unlike the upper layers, the MEC layer does not create a single PDU to pass to the lower layer. Instead, it defines subheaders that are used to combine multiple SDUs for multiplexing into a transport block to be transmitted through the PI layer. The main LCIDs are defined in a table like this. That's all for my presentation. Thank you for listening. It may not be perfect, but I hope it gave you a useful overview of what I've learned so far. If you have any feedback or would like to discuss further, please feel free to reach out via my LinkedIn. That's linkedin.com/in/Steve Yun. Thank you again.